Finally, in Chapter 13, we have colloids. Now, colloids are kind of an in-between state. They're in between a suspension and a solution. So a suspension would be something like sand and water, where if you threw a bunch of sand into water, the sand particles are so large and so much more dense in the water that they're going to settle to the bottom. And so there would be a separating out of the sand and the water. In colloids, the particles that you're mixing with the solvent are on a size or a scale in which they don't settle to the bottom of the solvent. They stay mixed throughout the solvent, part. But those particles are large enough that they interfere with light, and again, similar to solutions, there's numerous different examples of this. Now, this is the kind of thing where most people ask, like, for instance, well, what is whipped cream? Okay. Well, whipped cream, what state of matter would whipped cream be? Well, whipped cream is a colloid. So we can see it's even up here, I believe. Whipped cream's right here. Right. So it's classified as a foam, which is the solute-like particle is a gas, and the dispersing liquid or the solvent-like thing is a liquid. Okay. And you can see other things in here. Milk, for instance, is an emulsion. That's another type of thing that that we see. Paint. Paint's actually a solid that's not really dissolved in a liquid, but it's mixed in with a liquid. Marshmallows and all those kind of things. So there's a lot of interesting examples of colloids. One of the things you can do with colloids, or kind of a term or idea that you should be familiar with, is that colloids will exhibit what's called the Tyndall effect. So in the two glasses up on the top of the picture here, although it seems like you can kind of see it, but the one on the right, the beam of light that's coming through here, in theory, I don't think you're supposed to be able to see that. So this is a solution. So the light going through the solution, the particles in the solution are the solute particles are so small that you can't see those. The beam of light doesn't interfere with them, so they don't bounce off of them. You don't see them. However, in the mixture on the left, the particles that are mixed in with the liquid are large enough that when the light beam, the photons of light hit it, they bounce off in all different directions. And so some of them are going to come out of that beam, and you can observe those. The same thing happens in, like if you do laser, if there are fireworks or laser light shows, usually what they'll do is they'll have fireworks at the same time. So those smoke particles that are in the air from the fireworks will allow those beams of light from the laser light show to have something to bounce off of, so that they come back and they hit you in the eye so you can actually see them. Without that smoke in the air, the laser light show would be basically nothing. There would be nothing for the light to bounce off of. The other two pictures that we have in the on the board here, we have light shining through the trees in the forest, and again, the fact that you can see that light means that there's some particles in the air that light is bouncing off of. In this case, probably water droplets, perhaps on a kind of a misty morning, something like that. So whenever you see that, where you can see the rays of sun, is because there's some type of colloid particles, larger particles in the air that light can bounce off of and then come back to your eye. The other picture at the bottom here with the kind of spectacular sunset shows the effect of different wavelengths of light being basically diffracted as they go through the sky. So it's kind of an interesting effect that you'll learn about in physics if you haven't already done so. Colloids in biological systems also take on a rather significant that have a significant importance. Molecules are said to be either hydrophobic or hydrophilic. Molecules that have polar ends to them. So remember that organic molecules are by and large hydrocarbons, mostly carbon and hydrogen, usually a large degree of nonpolar parts to it. But a lot of them have polar aspects to them as well. So we look at something like this where you've got, at the top of this molecule is an amine group, an NH2, the hydroxyl group, OHs. So these things are all going to be polar. So this molecule that's shown here would probably be a hydrophilic type molecule, so it would dissolve in water. Might not form a solution. It would probably more likely be a colloid because of the size of the particle, but it would mix well with water. Obviously, hydrophobic things would be water-hating, and you can have both hydrophobic and hydrophilic within the same molecule, and depending on how it operated, whether or not the molecule would be able to dissolve in water or not. So let's see an example in just a moment. So here's sodium stearate. Sodium stearate is found in soaps, and what the stearate ion can do is the nonpolar part of this, right, that whole hydrocarbon chain there, can end up dissolving into an oil droplet. So it's the nonpolar part dissolving a nonpolar part, and what it does then is it leaves these polar ends coming out of the oil droplet. Well, that polar end then becomes more of a hydrophilic part where it's likely to dissolve in water. And this is when when you use soap to wash your hands, this is basically what you're doing, is you're taking any kind of oils that are in your hand and you're making them into hydrophilic type things so that they'll dissolve into the water. So it's kind of an idea of taking this hydrophobic particle and embedding these charged particles in it somehow to make it more hydrophilic so that it'll be able to dissolve. So that's our end of our discussion. So we'll do some practice problems in class, look at a couple more examples of colloids.